4.3, complements and conditional probability and Bayes' theorem. Key concepts as we extend the use of the multiplication rule to include the probability that among several trials we'll get at least one of some specified event. So at least one is going to be kind of a focus. We consider conditional probability, the probability of an event occurring when we have additional information that some other event has already occurred. So we've talked kind of about conditional probability a little bit. We'll get a little bit more into it. And then we also introduce Bayes' theorem. Complements and the probability of at least one. When finding the probability of some event occurring at least once, we should understand the following. At least one has the same meaning as one or more. And the complement of getting at least one particular event is that you get no occurrences of that event. And that's going to be huge, okay? That is going to be, that is going to make a really difficult problem into a not so difficult problem. So there's a formula for that. Finding the probability of getting at least one of some event, says probability of at least one occurrence of event A equals 1 minus probability of no occurrences of event A. So sometimes you can see it written like this. Probability of the number being at least 1 equals 1 minus the probability of 0 things happening. At least 1 is not none, okay? If you have at least $1, that means you don't have nothing, okay? Number 1, accidental iPad damage. A study found that 6% of damaged iPads were damaged by bags or backpacks. Part A says if 20 damaged iPads are randomly selected, find the probability of getting at least one that was damaged in a bag or backpack. So think about what at least one means, okay? It means 1 or 2 or 3 or 4 or 5 or 6 or 7 or 20 are damaged, okay? So that's a really complicated problem to calculate directly. We'd have to find the probability that one of them is damaged, or means plus, probability is 2 damaged, or 3, or 4, or plus. It's going to be much, much easier if we just say it's not none, right? At least one is not none. So the probability that we're talking about greater than or equal 1 is going to be 1 minus the probability of none. So how do we find the probability of none? That's the question. It's going to be 1 minus something. So if you think about that, if none of the 20 iPads are damaged, let's think about one at a time. We can think about that as a blanks problem, I guess. There would be one blank for each of the 20 iPads, okay? The probability that any one of them is not damaged would be 94%. Probability it's damaged is 6%, so the probability it's not damaged is 94%. Basically, if all of them are not damaged, or none of them are damaged, we're going to end up multiplying 0.94 times itself 20 times. And so that's exactly what we're going to do here. The probability of having none damaged is going to be 0.94 to the 20th power. Okay? That's the probability that none of them are damaged. So 0.2901. 0.2901. So then, if it's not none, at least one means not that. Everything else but that. So we're just going to take 1 minus that number. .7099 or so. 0.7099. It's a very common skill to have in probability. Probability of at least one Same thing as saying not none. Part B says, is the probability high enough so that we can be reasonably sure of getting at least one iPad damaged in a bag or backpack? I don't really like this question because I feel like it's subjective. All right, but you're talking about 0.7099, about 70% chance. I'd say that's not high enough. Okay, 0.7099 isn't high enough to be reasonably sure. We need to check more. Okay, so, if you think about it, we just did 1 minus 0.94 to the 20th power when we checked 20 bags. Okay, so what if we checked 40 bags? If we checked 40 bags, then there'd be like a 92% chance. Well, if we checked 50, okay, check 50 bags, there's a 95% chance that at least one of them, right? At least one of them is broken. Let's see, what if we check 100? %99.8% chance of finding at least one that's broken. And that makes sense. The more you check, the higher that probability is going to be of getting at least one. Conditional probability. We've already actually talked about this, but it bears repeating. Conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. And we talked about this symbology right here, this symbol right here, that vertical bar. Probability of B given A is how we read that. Probability of B given A denotes the conditional probability of event B occurring given that event A has already occurred. So understand how to read that, how to say that, and what that means. Intuitive approach for finding P given A. The conditional probability of B occurring given that A has occurred can be found by assuming that event A has occurred and then calculating the probability that event B will occur. All right. I know that's kind of difficult, so think about giving you this example before. And if I said, let's calculate it, I'm going to pick one number. I'm going to pick one number, and the probability of picking an odd number, is 3 out of 5. And that should make sense. That's a simple part over total. But then conditional probability means we've got this extra background information. What's the probability of picking an odd number given that I'm looking at a square? I told you I've got a square in my hand. I picked a square. What's the probability that it's an odd number I'm looking at? Well, we'd only have 2 squares to look at. So the probability of getting an odd number given that it's a square is 1/2. And so it's different. I'm still calculating the probability of finding an odd number, but now I've got this extra background information. That's conditional. So formal approach, it's a formula. Probability of B given A can be found by dividing the probability of events A and B both occurring by the probability of event A. So we've got this formula. I guess what you would pay attention to is this matches with this, okay? Probability of B given A is going to divide by that. It gets kind of confusing. You're like, which one's which? And this could be interchangeable. A and B is the same thing as saying B and A. If I said, you and me, or me and you, maybe that's grammatically incorrect, but we're talking about the same thing, the two of us, right? Doesn't matter which order that top is, but the bottom does matter, and it's got to match with whatever this is. Example 2, pre-employment drug screening. So you've got this chart, and it shows some employees, I guess, that either use or do not use drugs, as well as their test results, positive or negative. You notice you've got some false positives, you've got some false negatives, so sometimes the test isn't accurate. True positive means they use drugs and it showed positive. A true negative means they don't use drugs and it showed negative. So true means it's a good test result. False means it's a bad test result. If one of the 555 test subjects is randomly selected, find the probability that the subject had a positive test result given that the subject actually uses drugs. That is, find probability of positive test result given that subject uses drugs. Okay, so I'm gonna take this and I'm just gonna rewrite it, shorten it, I guess. Probability of positive given that they use drugs. So I just kind of abbreviate or shorten it a little bit. I guess you could use A and B if you wanted to. It gets a little bit confusing when you use abbreviations. So I would rather use something descriptive. Okay, so the formula says it's the probability of the and divided by the probability of the second one, use drugs. We are talking about probability, so we are still talking about part over total, by the way. But what we would do is this. We would say, okay, look at the number of people that use drugs. Okay, see how there are 50 people that use drugs. 45 plus 5 is 50. All right. Now think about the people that are positive and use drugs. 45 people are both positive and use drugs. So you should be able to kind of see that answer out of this. Okay. There are 555 total people in this. So the probability of being positive and use drugs is 45 out of 555. On the bottom, the probability they use drugs, well, there are 50 of those people out of the 555. Now, a little bit, I think this is silly to write that step because I feel like I've wasted a little bit of ink or something, because those 555s are going to cancel out. Essentially, all we're doing is taking 45 out of the 50 total. And that's what this reduces to anyway. 45 out of 50. You can reduce that fraction if you want, or you can type that in on a calculator if you want. 45 out of 50. Nine-tenths. Okay. Probability that a person tests positive given that they use drugs is 0.9. Now part B says, let's skip all the words, just go down to the bottom. Find the probability that they use drugs given that it's positive. Is that the same thing as what I just found? It's not. That is not the same thing as what I just found. Use drugs given positive is not the same thing as positive given use drugs. So be careful there. So according to the equation, you've got to do the and, use drugs and positive divided by the second one, positive. Not the same thing. So if you go back to that chart, we want use drugs and positive. Use drugs and positive. Use drugs and positive is the same 45. Okay. But the bottom says the probability of being positive. Okay, so we've got part. Now we need total. Positive are these numbers right here. 45 plus 25 is what, 70? It's going to be 45 over 70. So according to the formula, Probability of used drugs and positive is going to be 45 over 555. Probability of positive is going to be 70 over 555. But I feel like we can skip that and go straight to 45 over 70. It's part over total. The part we want over the total thing, 45 over 70. About 643 or so, 643. Okay. Which leads us to the confusion of the inverse. Basically, those two things weren't the same. Positive given used drugs given positive, not the same thing. Okay, so that's what this says. In general, probability of B given A is not going to be the same as probability of A given B. It could happen. Occasionally it will happen, but for the most part, in general, those two things are not going to be equal. Okay, that's called the confusion of the inverse. Example 3, consider these events. D is it's dark outdoors. M is it's midnight. Ignore the Alaskan winter and other such anomalies. Find the probability of dark given midnight and midnight given dark. So probability of dark given midnight. So it says ignore weird things that could happen, like the Alaskan winter or some weird anomaly like a solar flare or a comet or asteroid or I don't know, or a fire. In general, yeah, it's dark. If it's midnight, we know it's dark. Dark given midnight is 1. Okay. Any given night, if it's midnight, you would expect it to be dark. All right. But then probability of midnight given dark is a completely different question. So we know it's dark outside. What's the probability that it's midnight? Well, it's not 100%. I don't know what it is, but it's not 100%. Okay. Is it, I don't know, is it 1 out of 10-ish? I don't know. I don't really know, but I do know it's not equal to 1. It's not 100% chance that it's midnight. If you go outside and it's dark, you're like, oh, it's got to be midnight. That's not how it works, right? Okay. So all this is to show those two things are not equal. Okay. Now, Bayes' theorem can get really confusing. If you look at these next couple of formulas coming up, it looks way more complicated than it actually is. Okay. But check it out. We extend the discussion of conditional probability to include applications of Bayes' theorem, which we use for revising a probability value based on additional information that is later obtained. And so the formula that this book likes to use is this one. And what I want you to pay attention to is the fact that we're calculating a conditional probability, A given B, but we're using the reversed conditional probability. That is a huge clue that this is a Bayes' theorem question. When you're reading through your problem and you want to find a conditional, but then your details give you the reversed conditional, boom, clue, Bayes. Okay, so you might want to write that down, that we are finding conditional using reversed conditional. That's probably the best clue to have to know how to deal with this. Because once you know it's Bayes, it's not that hard. But if you didn't know it was Bayes, this is going to be a struggle. Okay, so you got to identify this as a Bayes, and I think that's the best way. You're finding a conditional using a reversed conditional. That's the way this is. Okay, so when you look at the second equation, it looks a lot more complicated, but they're just breaking it down into kind of conditions, okay? Notice the first part and the numerator is the same. The only thing that's different is that denominator looks a lot more complicated. They introduce a symbol that's specific to, I think I cut and pasted this from the internet, but you see this symbol? And this symbol just basically means not A. We've seen not A written in a couple of different ways. We've seen it written as like A complement or A complement. We've seen it written a couple of different ways. This is more like what you'd see in a logic class, but all three of those kind of say the same thing, not A. And so how I read this problem is on the bottom, we're talking about either A or not A. So all that's doing is breaking it down into what could possibly happen, all right? Either A happens or it doesn't happen. That's the denominator. And so when you get more than two events, all right, got a little bit of a typo. I don't like how those F's, some of them are capital and some of them are lowercase. I don't guess it matters, but just they probably should all be either lowercase or upper. It doesn't, I don't care which. But when you see this, the denominator is just taking you through every different thing that could possibly happen in the problem, okay? And so it's not supposed to be complicated. It's not supposed to look as confusing as it does. And in fact, when I'm doing a Bayes problem, a lot of the times the more things that happen, the easier the problem can be, because it's more obvious that it's a Bayes problem. Number 4, interpreting medical test results. Assume cancer has a 1% prevalence rate, meaning that 1% of the population has cancer. Denoting the event of having cancer by C, we have PC equals 0.01. For a subject randomly selected from the population. This result is included with the following performance characteristics of the test for cancer. False positive rate is 10%, or positive given cancer not present. True positive rate is 80%, or positive result given that cancer is present. Find probability of cancer given positive result. Okay. I think there's a lot to take in this problem. So what I would strongly recommend you do is abbreviate. Basically, I'm going to take all of the words out of the problem. Okay, and I know right here is what I want to find. I want to find the probability of cancer given positive. That's what I'm trying to find in this problem. Okay, so I'm also going to go back and write down the things that they give me in this problem. So they gave me the probability of cancer was 0.01. False positive rate was 10%, so that was the probability of positive given cancer was 0.10. And then the probability that it's positive, oh shoot, I didn't see that, not present. Positive given not cancer. Let's put a little bar over it like that. Positive given not cancer, 0.1. And then positive given cancer is 0.80. Okay. Now, to me, once I write that down, I pretty much ignore the paragraph. I'm not looking at all the words. I'm just looking at what I wrote down. And it is a huge indicator to me that we're asking for C given positive, but they give me positive given C. When they give me the reversed conditional, I'm expecting this to be a Bayes problem. Okay? I'm expecting this to be a Bayes problem. So, we're finding probability of cancer given positive. So the top equation that I had you box in said that's going to be the probability of, I forget which order it was. It doesn't really matter. I like to write it in this order. I know the one you boxed switched those two around, but I like this because I am finding the probability of C. I'm finding the probability of C, but I'm using the reversed positive given C. And then on the bottom, it's the probability of positive, like that. Okay. So it's a little bit tricky here. They give me the probability of cancer was 0.01. So that's this right here, 0.01. And the probability of positive given cancer is 0.8. So this is 0.80 right here. But they did not give me the probability of being positive. They did not give me the one on the bottom, okay? But they gave me other stuff. They broke it down more than that formula does. This is actually, I'm going to use the second equation where it breaks it down. Because when it's positive, when something is positive, okay, either they have cancer or they don't. Either they have cancer or they don't. So what I'm going to do is I'm going to split this bottom part of this equation into two parts, okay? So when you think about being positive, so we can say the probability of having cancer times probability of positive given you have cancer plus, okay, so either you have cancer or you don't, right? Either you have cancer or you don't. And we're talking about the probability of being positive. So the only other case is if you don't have cancer, find the probability of positive given you don't have cancer. Can you guys see that okay? That green's kind of difficult to see. You guys all right? That's what could happen. I broke down probability of being positive into either you have cancer and it's positive or you don't have cancer and it's positive. So the top's still going to be the same. You're going to have that probability of cancer times probability of positive given cancer. So I can just fill in some of the numbers that I've got. So this one was 0.01 and this one was 0.80. Probability of cancer was 0.01. Probability of positive given cancer was 0.8. Notice that's exactly the same thing, and that should make sense because either you do or you don't. Either you have it or you don't, and we're finding the part where we do, okay? The one thing they don't seem to give me is the probability that we don't have cancer, but that's pretty easy to figure out. If the probability that you have it is 0.01, then the probability that you don't must be 0.99. And so that's what goes right here. Probability that you don't, we had to figure that out, was 0.99. And then the probability that it's positive given there's no cancer is 0.10. So, look at what we have. We have 0.01 times 0.80 over 0.01 times 0.80 plus 0.99 times 0.10. Part over total. Multiply that out. 0.01 times 0.8 is 0.008. So then you'd see that again. And 0.99 times 0.1 is 0.099. Use a calculator, that's going to be about 0.0748. So let's think about what we just found. The probability that you have cancer, given that it's a positive result, is only 7%. That's an interesting, think about that. If you get a test for cancer and it shows that you're positive, this is saying the probability that you actually do have cancer given that positive result is only about 7%. Okay, so get another test, get a second opinion or whatever. So that's an interesting result, I think. Prior and posterior probability. A prior probability is an initial probability value originally obtained before any additional information is obtained. Okay, this is probably, when you think about probability, this is probably what you think about. Posterior probability is a probability value that has been revised by using additional information that is later obtained. Okay, posterior, something about information that's obtained later. Relative to the last example, probability of cancer is 0.1 or 0.01 or 1%, which is the probability a randomly selected subject has cancer. This is an example of a prior probability. Go back and look at the definition. Obtained before any additional information is obtained. Using the additional information that the subject has received a positive test result, we found the probability that C given positive test is 0.0748, and this is a posterior probability because it uses that additional information of the positive test result.